Okay, so let's come back to our class. So basically, in the last lecture, we have been further talking about, basically in the last hour, we have been further talking about the details of NP completeness. So basically, we have this two theorem that actually we show that, in general, for NP complete problem, if you can solve an NP complete problem in polynomial time, if and only if P equals to NP here. And furthermore, another theorem that we show that assume that we have proved that the problem y here is an NP-complete problem. And furthermore, we know that there is another problem z, which is still an NP problem, problem that there is actually a reduction from y to z here. So this is actually also going to establish that z is an NP-complete problem here. So furthermore, I guess a very fundamental question here that we would like to ask is actually, do there is like a natural NP-complete problem? So here, for instance, a very important problem that we actually have been just talked about is the circuit set problem. Where in general, we want to talk about like a combinatorial circuit built out of an AND or a NOT gates. And actually, for that circuit, maybe some of the part is actually given by hard-encoded inputs, and the other part is actually given by inputs. Basically by variables that you can choose here. So Cook and Levin proved this, and this is actually known as the Cook-Levin theorem, that the circuit set problem is actually an NP-complete problem. And furthermore, there's a polynomial time reduction from circuit set to three set, so that the three set problem is an NP-complete problem. So I think to finish the proof of the Cook-Levin theorem, we first need to prove that the circuit set is an NP-complete problem, and this is what we have been talking about. So this part is actually based on a relatively straightforward fact that actually we didn't cover all of the details, but you can imagine that for an arbitrary algorithm here, if the algorithm takes poly n steps, and we know that actually the AND, OR, and NOT gates, they're actually universal. So as long as you have like a polynomial time algorithm for like a problem here, and actually it takes like poly n steps, we know that we can correspondingly have a circuit that using this AND, OR, and NOT gates, which is actually of poly n size. So this is something standard in terms of designing algorithms. And basically, we based on this fact, we can establish that. Just based on the discussion here, that actually, basically for a problem which is in NP, where basically we have two inputs actually, and S is like the input string for the polynomial time verifier, and the T here is a certificate. This is just like the S part. The S part is just like being the hard encoded inputs, and the T part is basically the variables that you're going to choose. You're going to choose this such that you need to return like yes for this polytime verifier here. So furthermore, I guess maybe to further explain the problem here, that actually we make a example that basically we talk about this very specific case where we want to ask like whether a corresponding graph is actually contain a two-node independent graph or not. A two-node independent set or not inside a graph here. So basically a specific instance we are actually talking about, maybe for instance, let's just consider a case where n equals to 3 here. So when n equals to 3, maybe we can consider like a graph here, for instance, if in this graph, like UVW. In any case, as long as we have an n-node graph, this graph have like n choose 2 number of edges here. So basically we have this number of nodes, these n choose 2 nodes represents the status of the edges here. And also there are n nodes that represents the certificate, that whether actually we choose the vertex or not, because we are actually talking about like a two-node independent set. So basically we correspondingly construct a circuit that basically the circuit has two parts. So for the first part, actually we need to understand whether at least two nodes in T are actually set to 1 or not. So basically this is this question that basically this question that in this part of the circuit that we have been talking about. And the other part is basically we want to answer like actually whether a two bits in T are actually both set to 1 if they are actually come from two ends of the same edge here. So basically, this part, we have like a negative answer. Basically, as long as it is actually a valid independent set, we are basically, if and only if we are going to have like a 0 answer to this question. So this actually make the whole construction of the circuit that it suffices that we have like a NOT gate here to turn this into a 1. And basically the value here that we are going to return here to be a 1, if and only if both parts, basically this returns 1, this returns 1, which means that before the NOT, actually it is a 0 here like this. And actually this is just like a complete circuit to actually test whether like a 3-node graph is going to contain a 2-node independent set or not. And basically, and also on the other hand, we can clearly see that in general, for general n here, this is a circuit of poly n size here. And actually, this finishes the construction of the circuit for this specific problem. Okay, so this, for the Cook-Levin theorem, this just finishes the first part. So furthermore, basically in this hour, we will prove that the circuit set problem can be polynomial time reduced to a three-set problem. And this is what we need to do to finish the proof of the Cook-Levin theorem. So before we do that, is there any question for the last hour? Okay, so if there is no question, let's finish the proof of the Cook-Levin theorem. So as we just discussed, so basically it remains to prove actually the circuit set problem. The polynomial time reduced to the three-set problem. So basically, the proof that we will actually going to give here is going to be composed of two parts. So here, we will not make a direct polytime reduction from the circuit set problem to the three-set problem. So because the circuit set problem is like a problem about circuits, and three-set problem is talking about like CN formulas, where each formula is going to have exactly three literals. So these requirements are a little bit different. So we will actually make another. We will discuss another problem in the middle to actually make the reduction easier for both sides. So basically, for the first part, we will prove that actually for an arbitrary circuit set instance. So basically, we can construct an equivalent instance. An equivalent instance of set in which each clause contains at most three variables. So we will first, make a reduction to a problem that is a little bit different from three set. So basically for the three set, as we just mentioned, each clause is going to have exactly three variables. So in this first reduction, we are okay that maybe some of the clause has one or two variables, and then at most three variables. We will first make a reduction on this. And basically for the second part, we then actually, excuse me. So basically after doing that, we then convert this problem, basically this set instance, to an equivalent one. Basically now inside each clause has exactly three variables. I think each clause is exactly three variables. And this is, just according to the definition of three sets, so this is basically going to be an instance of three sets. And then we finish it. We finish the proof here. So for the first part, I guess here, for the first part, basically we have an arbitrary circuit set instance. So here, let's say that we are going to first prove the first part and then prove the second part. So for the first part, basically we just consider an arbitrary circuit K. So what we do is that we actually associate a variable xv with each node in this circuit K here. So basically this is to, formally speaking, this is just to encode the value that the circuit holds. at that node. So basically we have all these kind of nodes. So this is not only about like the nodes at the very bottom, about the input nodes, but actually for all of the nodes here, we actually are going to store a corresponding value on xv here to represent basically the value that actually the circuit holds at that place. So this is actually an important idea that actually having this kind of variables, and actually we are going to make these variables to be the variables in a set problem. I mean, not like a circuit set problem, but actually in like a three set problem and this kind of things. And we are actually going to make like the variables xv here at each place of the circuit, each node of the circuit. We are going to turn this into something in a class. So this is basically what we need to think about. Actually, this is important thing that we are actually going to make the reduction here. So in particular now, let's define the clauses. So the clauses of the set problem. So let's do this. So on the one hand, so basically we know that we need to make all the computations correctly. So basically we need to encode requirement that the circuit computes value correctly at each gate. So that is basically to say we need to figure out what we do at each of the AND or and NOT gates. So basically, I see there will be three cases. I mean, basically AND or. So we do this. So if a node V is actually labeled with NOT. So basically, this is the notation of NOT. I mean, if it's labeled with NOT, it has actually only one input, and actually it's only entering edge is from U. So that is basically saying we are having a case where we have a NOT like this, and we are actually marking this as XV. But actually, we know that the input is actually coming from XU. So basically, this is the situation that we are actually talking about here. So basically, in this case, we actually need to have that actually XV equals to the NOT of XU here. So we will need to think about, I mean, in general, to promise that XV equals to the NOT of XU. This is something happening in the circuit. On the other hand, we can make some promises by cleverly choosing the clauses that we use here. So we say that actually we can guarantee this. We add three clauses. Sorry, we add two clauses for this case. So for this case, we add two clauses. We do this. So we add XV or XU. So recall that in general, for like a set formula, we require that inside each formula, we are going to have OR conditions. So basically, we have an OR condition here. So we have two clauses. So one of them is going to be XV or XU. And the other clause that we are going to have is not XV or not XU. So these are the two clauses that we are going to add here. And we need to think about, I mean, why do we actually want to add them? So basically, I mean, in the case that actually, if both of them are correct, so basically we say that actually XV or XU equals to 1 and 3. So basically, we need to satisfy all the clauses, and we see the case where actually both of the clauses, they have the value 1 here. So if this is the case that XV or XU equals 1 and not xv or not xu equals to 1. So we know that we are going to have the value pair is xv xu is going to be 0 or 1 or 1 0. Otherwise, if it is a 1 1 pair, I mean, if they are actually a 1 1 pair, this is going to be 0. If it is a 0 0 pair, this is going to be 0. But on the other hand, you can check 0 1 1 0. They definitely just, for instance, if it is like a 0 1 pair, this is a 1 0 pair. So it is going to be give you a value 1 here. So nevertheless, having the assumption that actually xv or xu equals to 1 and not xv or not xq equals to 1, this is just going to imply that xv is the not of xu. Okay, so any question about this, the thing that we add here for a not a node here? Okay, so I think this is, I mean, for the not case, this is relatively straightforward. So we still need to deal with the case where we have a AND gate or a not gate or an OR gate here. So let's say maybe we want to consider like an OR gate here. So if a node V is labeled with an OR here, and we say that it's two entering edges are actually from nodes U and W. So that is basically saying that we have an OR gate like this, which is basically going to be XV. And we have some XU and XW here. So in this case, I mean, basically based on the definition of an OR gate, basically we need to have XV. I guess this V is not writing so good. So here it is. Here it is a V here. This is also V here. So basically we need to have that XV equals to XU or XW. So basically here we can guarantee this by adding 3 clauses. So here the clauses we add is these 3. So we have this XV or XU naught and an XV or an XW naught. And the other is the XV naught or XU or XW. So these are the 3 clauses that we actually add here. So an argument that we can make here is that let's do this. So if basically basically in the set problem, we need to make sure that all of them are equal to 1 here. So let's see what is going to happen if they are all equal to 1 here. So basically. And not XV. So we consider something like this. So if XV equals to 0, so this is 0 and this is also an XV here. And XV here is 0. So this is just going to imply that actually XU, not XU and actually not XW, they must equals to 1, and this is actually going to imply that actually XU equals to XW equals to 0. So this satisfies the case that actually what we want, basically XV equals to XU and XV equals to XU or XW here. So basically they satisfy what we need. And on the other hand, so if XV equals to 1, so if XV equals to 1, the place we are looking at is basically this clause. In this case, we know this value equals to 1. sorry, this value equals to 0, and basically we need to make sure that this part of the clause must equal to 1 here. So if xv equals to 1 here, basically the third clause gives xu or xw equals to 1. So in any case, I mean, either the case xv equals to 0 or the case xv equals to 1, we know that actually xv equals to xu or xw. So basically this finishes this part. So is there any question for this, for like an or a node here? Okay, so the only remaining thing here that we need to probably need to reopen this. So the only remaining thing that we need to think about is the case where actually we have a node which is labeled as end. So basically, I mean, this end part is quite like the or part, but it's just like a lot of places with negation here. So let's actually write everything down here, and it's two entering images from nodes. Still, we use u and w here. So basically, here we are going to have an AND gate, which is the xv, and we are going to have xu, xw here. So basically, in this case, then we need to have xv to xu and xw. So basically, in this case, we guarantee this. We actually are adding also adding three clauses here. So the three clauses that we add here is that here we have like a not xv or xu, and we have a not xv or xw, and we have a xv or not xu or not x. So we clearly see that this is just a direct negation of all the clauses that we use for the OR case. And I guess you can just check by yourself that actually basically this, I mean, as long as all of these three clauses are equal to 1, they are going to promise that xv equals to xu and xw here. So basically, I mean, this is just very similar to the OR case. So we just say that this proof is similar to the OR case, and I guess you can just check this by yourself. Okay, so this actually finishes the computation part. I mean, basically for a circuit set problem. I guess, for instance, maybe for this circuit set problem. So we have successfully transferred all the like AND, OR, and NOT gates into Boolean formulas that we need to satisfy. But I guess this is probably still not the end of the story. So we also, on the other hand, we need to take care of the inputs and outputs. So this is the part that we also need to give a brief discussion. So we say, on the other hand, basically we need to guarantee that the hard encoded constants other sources have their specified values. And actually, we also need to check that the output evaluates to 1. Okay, so how do we do this? So we still have actually some kind of way to do this. So basically, let's say that for a source, basically for input source node V with labeled, let's say 0, or respectively we 1. So this is actually the same. So we will actually add a class with the single variable. I mean, just a class with a single variable, just one, like a literal here. So we just, I mean, we want to make sure that one of the value just equals to 0. So we just add xv naught here. So, I mean, this is one of the clause. And to make this clause equals to 1, we know that xv must equals to 0. Or respectively, I mean, we say, if we want to, I mean, have this kind of hard encoded constant, I mean, if we want to have like the value of xv equals to 1, we just add this clause, just add xv here. So it must equals to 1, I mean, based on a restriction of the set problem. I mean, we say that this just forces xv to take the designated value. Okay, so this is just a way that we actually do the hard encoded input. So basically for the variables, so basically for this part, I mean, as long as they are actually question marks, so we don't have any further restriction, it can be either 0 or 1 here. So we just make, I mean, because this is just like a certificate, we need to figure out what is actually a solution for that. So I mean, if just like we have a question mark for a variable here, we don't need to make any change. I mean, it can be either 0 or 1 here. But what is important here is that basically for the input here, we need to have like this kind of encoding for hard encoded input. So if it's specifically need to be 0 or specifically need to 1 here, we need to add this single variable clause, this xv bar or xv naught or the xv here. So basically this is the thing that we need to do here. And I think at the last, we need to have like an encode for the output. So basically for the output node. So the output node typically are denoted by let's say like O here. So basically we add the single variable clause. Just XO. Which if this is just like a single variable clause here, this is just going to require that XO. Okay, so basically this finishes our construction here. I mean, this finishes our construction. We want to make a reduction from a circuit set problem to a set problem where each clause has at most 3 literals. So basically this is the whole construction. So is there any question about the construction here? Basically how we want to find an instance. I mean, an instance in a set problem that corresponds to, basically for an arbitrary instance of a circuit set problem, we can correspondingly find an instance of a set problem where each clause has most 3 literals here. Is there any question for this? Okay, so if there's no question, the next thing, I mean, as you can imagine, what we need to prove next is actually that the given circuit set problem, the given circuit set instance is actually equivalent to the constraint. Sorry, to the constructed set instance, to the constructed set instance that we just made here. So we say that this is actually equivalent. So we also need to show the directions from left-hand side to the right-hand side, and also from the right-hand side to the left-hand side. So let's first do a left-hand side to right-hand side. So basically, given like because here it's just like we are given like a certain set instance, and we need to show that basically we can it's the value of this satisfiable circuit is actually can be given by the constructed set instance. So let's say that we are given the satisfiable circuit. Okay, so basically, because all of the previous part, so basically we have finished all the parts about like the inputs, hard encoded inputs, outputs, and also the calculations of the AND or NOT gates. So basically, we can make sure that actually the satisfying assignment to the circuit is just like it's going to the circuit inputs can actually we just do like can be we just do like the calculation. So we say just we do the this can be propagated to create values at all nodes in K. So by like a propagation, it's just like, for instance, here, at the very bottom here, we have all these values. Assume that we have like a satisfiable assignment. So here, a satisfiable assignment is that we pick the U and W here to be the two node independent set here. So we can have like a 1, 1, 0 here. So having this kind of assignment, we just propagate all the values. So for instance, we just can calculate, okay, so this value, so basically this value is actually a 0, and this value is actually a 1, and this value is actually a 0. And we do this for all parts of the circuit. So we know that if this is like a satisfying assignment, and we just, because like the circuit is only going to have polynomial size, so we can do this kind of propagation. And basically the overall calculation time is going to be polynomial. So basically the calculation time is actually, still polynomial. And actually, we know that based on the correctness of our construction for the input, for the output, and also for the AND or NOT gates. So this is actually a set of values satisfying the set instance be constructed. So this is the argument from left-hand side to the right-hand side. So basically from the right-hand side to the left-hand side, this is actually quite similar. So suppose that the set instance constructed is satisfiable. So what we do is we just like look at the values of the variables corresponding to the circuit its inputs. So basically we say that these values is just going to give a satisfying assignment for the circuit K. For the circuit K here. I guess this is just straightforward. It's just because the the set clauses is just like going to ensure that basically the value assigned to all the nodes of the K here is basically just what the circuit computes. Because as we just mentioned, we have actually a carefully constructed all like this kind of like AND or a NOT gate. So basically to make sure that as long as I guess we have like a set instance that actually it is satisfiable, we just return all these values, and this is just the correct values for the circuit here. In particular, we look at the inputs, and this is actually going to give you like a satisfying assignment for this circuit set problem. Okay, so is there any question for this proof? So basically, we show like the equivalence, between the circuit, an arbitrary circuit set instance and to the corresponding constructed set instance that we make here. Okay, so the last thing that we need to do here is just going to be prove the second part. It's basically going to prove this. So basically, we now here we have already transferred, a circuit set problem, which is probably what we are less familiar with, to a set problem. Basically, have like this kind of clauses and variables, but inside each of the clause, the number of variables is at most 3, and this is slightly different from a normal definition of a set where we require that each clause has exactly 3 variables. So here we need to finish this part, and actually we need to finish the construction. So basically, this is some like a further construction that we are going to make, that will actually make some reduction. Basically for the clauses with only 1 or 2 literals, we are going to maybe have a little bit more literals and actually make sure that all of the clauses are going to have exactly 3 literals. So we prove the second part here. So basically, what we do is just that we just convert this instance of set to an equivalent instance. In which each clause has exactly 3 variables. Okay, so to do this, we have some further, we basically borrow a few further variables here. So in particular, we have 4 of them. So we say that to do this, we create 4 new variables. Basically, let's say they are Z1, Z2, Z3, and Z4. So the idea is actually to ensure that in any basically we will have some kind of, we just make these variables, but actually some of them are actually dumb. Dumb in the sense that basically they have some kind of designated values here. So basically, we have maybe, for instance, we have like a xi, for instance, like or xj here. But if currently it is like a clause with length 2 here, we can feel free to just have like a or 0. So this is not, it's not going to influence what the clause is, but this is actually going to further fulfill the condition that we are talking about, a 3-set problem, instead of like a set problem where each clause has length at most 3 here. So basically, we are going to have some kind of dumb variable such that their value are enforced to be 0 if it is a satisfying assignment. So this is the logic. And if here, for instance, like if you only have like a one variable in one of the clause, recall that basically when we consider like the inputs, so basically when we consider inputs and output, we do have clauses where a clause can only have 1 literal. So maybe we also want to have this kind of or 0 kind of things. So basically we want to construct, 2 zeros, based on this kind of restrictions. So in particular here, we want to specifically in this kind of satisfying assignment, we want to restrict such that actually z1 equals to z2 equals to 0. So we are going to borrow 4 variables, and actually 2 of them are going to be enforced to the 0, and the Z3 and Z4 here are actually used to enforce that this is actually on Z1, Z2, they're actually equal to 0. So let's see how to do this. So this is actually achieved by adding 8 clauses. So what do we do for this? So we add such kind of 8 clauses. So we have this Z1 bar with Z1, I say like a bar of a variable just means a not of a variable. So like a not of Z1 or a Z3 or Z4. And basically, we just go over all the possible choices of the Z3 and Z4 here. So basically, we also have this. And we have this. And we have this. And similarly, we do the same thing for the Z2 here. Excuse me. So these are the choices that we make for Z1, Z2, Z3, and Z4. So the key observation here is that basically here, I mean, we just enumerate all the possible choices for the Z3 and Z4 here. So the point is that no matter actually how we choose Z3 and Z4, one of Z3 or Z4, 3 or Z4, Z3 or Z4 not, and Z3 not or Z4 not is 0. And this is just going to enforce, I mean, if all of them, they are 1 here, this is just going to enforce that actually this Z1 not and Z2 not, they must be 1. And just means that Z1 and Z2, they must be correspondingly be 0 here. So this is the reason that we actually add these 3 clauses here. So, and actually we know that after having this kind of a construction, now, so this is really straightforward then. So basically for each clause in the set instance with a single key, we just replace it by T or Z1 or Z2. And furthermore, for each clause in the set instance with 2 terms, let's say T1 or T2, we replace by T1 or T2 or Z1 or Z2, whatever. This is not so important. And actually, we just clearly see that basically this for this resulting 3 set formula, for this resulting 3 set formula is clearly equivalent to the set formula. With at most 3 variables in each clause. And this just finishes the whole proof of the Cook-Levin theorem. Question ended. Okay, so I think we basically finishes the most important thing that we want to prove in complexity theory, the Cook-Levin theorem. Basically, the 3-set problem is an NP-complete problem. So is there any question about like any part of the proof that basically this is really like a long proof that we first have the part that we want to reduce any NP problem to a circuit set problem. In general, we establish the NP completeness of a circuit set problem. But this is still a little bit artificial, and I mean, this is not so clear how we are going to further use this. So basically, we then make a reduction. I mean, we make a reduction from a circuit set problem to a 3-set problem, and due to the NP completeness of the circuit set problem, we establish the 3-set NP completeness of the 3-set problem. And this construction is basically made by transition that in the middle we have a problem, or we have like a set instance where each clause has at most three variables, and to make the transition from the circuit set problem to this kind of set problem, we just correspondingly we mark all the variables in this circuit, and we make this kind of like a clause. Basically we make this a set instance, and we further make a little bit of construction that as long as for your set instance where each clause had most three variables, so we can add like four extra variables, z1, z2, z3, and z4, where the z1, z2 are enforced to be 0, and basically we can just fulfill all the clauses where only have like one or two terms, and we can make all of the clauses then have exactly three terms and make it exactly as a three-set problem. So this is just like a proof sketch, and basically for the past 1 or 2 hours, I've been basically covering the details for the proof of this Cook-Levin theorem. So is there any question about the Cook-Levin theorem? Excuse me. So here, so one student asked a question about like what Z3 and Z4, they are for here. So the Z3 and Z4, they are like basically like a free variable here. So basically we don't need to like further enforce like what the values of Z3 and Z4 here, but their existence actually ensures that the values of Z1 and Z2, they must equals to 0. So that is basically in this part of the 8 clauses here. So the point is that no matter like what is the choice of the Z3 and Z4 here, so let's just feel free to say that, for instance, like Z3 equals to 1 and Z4 equals to 0. So let's say that Z3 equals to 1, Z4 equals to 0. But actually you have this part. So you have this not Z3 or Z4 here. So actually in this case, both of them, they are exactly 0 here. So basically, to make sure that this is, you have this clause, assume that you have this clause that you have chosen here. So if you choose this clause, if you say that this is a satisfying assignment, it must be the case that this clause must equals to 0. But the Z3 here is, Z3 not here is a 0, and the Z4 here it is actually a 0 here. This is just actually enforce that the not Z1, they must be 1. The not Z1 must be 1 just means that Z1 must be 0. And actually, similarly, for the similar reason, Z2 must be 0. So the Z3 and Z4, their existence just to ensure, basically having these 8 clauses just to ensure that the value of Z1 and Z2, they must be 0. So is this getting more clear to you? They are actually used. They are actually used here. You should have like all these 8 clauses enclosed in this construction here, but their value is arbitrary. Here. So, okay. So any other questions? Okay, so I have like 3 or 4 minutes for this hour. So let's actually make some very brief discussion here. So let's make a quick summary. So as a summary, so we have the following high-level picture of NP-complete problems. So basically, because we have actually established chains of reductions of problems, so we basically can draw the things like this. So here, some of the problems, they're actually marked in red colors. So because, we only have limited time in this class, and there are like just so many problems and so many reductions. So we use red colors basically for problems we don't have time to cover in class. So the core of everything is basically the 3-set problem. And this is actually the NP-completeness of the 3-set problem is actually established by the Cook-Levin theorem. And actually, a complete chain that we have been talking about is the independent set problem. And then to the vertex cover problem. And then to the set cover problem. So this group of the problems are typically called packing and covering. And we have some other chains of NP-complete problems. So for instance, like in some graph problem, so there is like a directed Hamiltonian cycle problem, and also a Hamiltonian cycle problem. So I guess I will probably just mention the name of this NP-complete problems. And if you're interested, you can just, for instance, check Wikipedia or check our textbook, the Kleinberg-Tadeusz book. So there are some discussion along this. Or like the traveling salesman problem. This is a very famous NP-complete problem, actually. So this is typically called the sequencing problems. So we actually, in our lecture, we proved that actually the graph, a three-color problem is an NP-complete problem. So basically, we make a reduction from three set to the graph three-color problem. So actually, it can be further make a polynomial time reduction to a problem called a planar. I mean, we assume that actually we have a planar graph, and we ask like whether planar graph is three-colorable or not. And this is typically called like a partitioning problem. Partition. I guess the spelling is, let me correct the spelling here. So partitioning problem. And furthermore, for instance, I mean, there are also like a subset sum problem. And for instance, I mean, we have talked about some weighted interval scheduling problem, but actually for a lot of scheduling problem, it is in general quite difficult. And such problem becomes to the category of numerical problems. Okay, so there are just so many problems, so many NP-complete problems in different, domains. I mean, it's not necessary to be like Boolean problems, but can be graph problems, can be scheduling problems, can be in general for a lot of different domains. But in general, I mean, all this kind of NP-completeness of a lot of problems can be established by all these kind of reductions. And we say that basically in our exam, I mean, we will definitely have a problem to examine, to show some problem. I mean, the proof should not be too difficult, but to make sure that you have a good understanding about what NP-completeness is. So in our example, I mean, when you do this, it is okay to use the NP-completeness of these problems and make reductions. Basically, I mean, because there are many different NP-complete problems here. Okay, so let's take a brief break and let's come back at 10 over 5 here.